Hi everyone, I'm here today with Dr. Melanie Kothup. She is the director of the Bionics Cluster at UCF, and she is also a renowned scientist and researcher. It's a pleasure to have you on this month's Kismet Tech Talk.
Thank you.
And let's start with the basics, just helping the audience understand, your luminous background in cell biology. So let's talk about your background first, just who you are and what you've done.
Okay, so I actually grew up in North Wales, so I'm a rural girl, and then left to do my BSc at the University of Liverpool. So I did medical cell biology. Started off with biochemistry, didn't like it so much, and then moved to medical cell biology, and then moved to London. I did my PhD at UCL, University College London, based at the Royal National Orthopaedic Hospital at Stanmore. And the goal and the focus of that work was really interdisciplinary. It was to work, alongside engineers and the surgeons and clinicians in order to facilitate new implants, new technologies. And it worked really well. I think that the department is well known there. And then in 2017, I left to come to UCF, who were looking to start a similar thing, that interdisciplinary research where you combine engineers, material scientists, clinicians, biologists such as myself. Yeah. And it was great because it was a new department, it was a new place. I guess for me, it's a new thing to build, to help to create, and it was very attractive. So I came here then. And so that was the Bionics cluster that formed, and originally called the Prosthetic Interfaces cluster, but changed to the Bionics. See if I remember, bionic implants, materials, and interfaces. Yeah. And so we have faculty from a range. It started from the College of Medicine, faculty based at mechanical and aerospace engineering, and then materials and science engineering. But more recently, we've had faculty join from chemistry, Limitless guys, Nicholson Communications Department, and the College of Nursing, as well as some surgeons from Advent Health as well, and more. So it's growing nicely, it's exciting, and that brought me here.
Yeah, so very interdisciplinary, industry focused, and focused on solving broader issues within healthcare. Yeah. So we're here to talk about the publication earlier this year in Nanozymes and Biomaterials. So let's talk about what are biofilms. So for our audience, what is it? Why is it an issue? And why is it such a big problem on high-touch surfaces?
Okay, so we have so many different types of bacteria, and not even talking about the viruses, but and the fungi, but the bacteria. But one of the common things that most of them do is to protect themselves. They're phenomenal. I think they're phenomenal in many ways because they can change their structure, their DNA almost to change according to the environment, so they can be very tricky. But one of the other things that makes them very difficult and challenging and tricky is they form this biofilm. So they exude this kind of slimy matrix and they embed themselves in it. And from that, it protects them, it becomes a barrier. So you give systemic antibiotics or sprays or something on a surface, it needs to penetrate that biofilm to get to the bacteria inside. And when they're inside as well, they become quite difficult to kill because their metabolism slows down, amongst other things. And so it can be really challenging to treat them. So if you can break the biofilm and get to the bacteria inside, then that would be fantastic. But unfortunately, not a lot of products are able to do that. So we have this biofilm that can hang around for long periods of time. The bacteria can control it and release themselves from it at any given point and then reinfect a surface or a person. So it's a real challenge to get past that biofilm.
Yeah, and bacteria are good at, they're survivors. And so when we think about, so a lot of people think, if I don't see anything on the surface, I've cleaned it, I'm fine. Why might that be an issue, like let's say in healthcare where biofilms tend to be more rampant?
Okay, so what happens is that the biofilm is still there even though we can't see it. And so then if you're in a hospital or various other places where there are lots of people touching surfaces, you can then put a bacteria on that surface. Or if the bacteria is still on that surface, you can then touch that surface and then infect yourself with that bacteria. And you won't know because you can't see. And a lot of the products, I might be going off target with the question. That's okay. I'm blanking on what the question was. But so it was about the bacteria on the surface, wasn't it? So then if you have if you have the bacteria on the surface, then people can touch it and infect themselves, and you won't necessarily know. So you need to have a coating or a spray or a product that gives confidence that that surface is protected, no matter how many people touch it, with different bugs and different bacteria.
Great. Why do biofilms resist traditional cleaning? I think that's something that the public and even some people in healthcare maybe don't fully understand. Why is it such a hard, you've touched on different points of that, but just kind of at the heart of it, what is it about biofilms?
I think with the biofilms, they're a fantastic barrier. They're impenetrable. So you can put products on that surface, but it doesn't necessarily remove the biofilm and therefore attack or kill the bacteria. And if it does, it may just do it a little bit. I mean, you've got various layers of the biofilm as well. And so you need a product that's able to completely eliminate that biofilm and not just maybe scratch the surface, for want of a better word.
Gotcha. Yeah. All right. So earlier this year, you published a paper in Biomaterials on how the Nanozyme works. So could you just talk a little bit about how the silver, ceria, Nanozyme, that combination makes it effective as an antimicrobial?
Okay. So it was a really interesting paper and really fantastic working with you and others in the team as well, because it was such a journey to work out what might be happening. I say might, just scientific disclaimer, what appears to be happening. Initially, we thought that it was attaching onto the surface and it was breaking the wall. And we thought initially, at least I thought initially, it would be your light activated free radicals. But then as the study went on and as the questions accumulated, we started doing more and more experiments and found that it seems that the most important product that's formed is hydrogen peroxide. And exactly how the silver and the cerium are working to really boost the production of the hydrogen peroxide is still a little, needs to be discovered a little bit more. But it seems to be a perfect kind of synergy between the silver and the cerium that kind of changes the electron exchange on the surface, and you get this amount of hydrogen peroxide that's formed. And that seems to be the key element that causes bacterial death or bacterial suicide. From what we can see.
So when you read the paper through the scientific jargon, it is eventually programmed death or bacterial suicide. Yes. So thinking about, the Nanozyme and how that works, how would you compare that to like a disinfectant chemistry like hydrogen peroxide when you're thinking about how effective it is against a biofilm, for example?
Okay. So I think that with the nanoparticle, one of the key things that's fantastic, I think, is the auto-regenerative component of it. It just keeps recycling and producing more and more, which the other chemicals don't do. So that when it's on a surface, it keeps on going. And so you're able to get rid of that biofilm layer way more effectively than other products that are out there at the moment.
Great. Yeah. And then, we joked slightly about the programmed death in bacteria. So what is happening at the microscopic level? There's a great discussion of that in the Biomaterials paper, but in a just kind of like broad sense, what is actually happening?
Okay, what I think is happening, what I thought initially, what we saw initially was that, as mentioned, the nanoparticles seem to attach onto the surface. And initially it was thought that the cell membrane, the bacterial membrane was breached, and then you'd get the influx of fluid into the bacteria, because what we were seeing was that the bacteria were just starting to lose shape and just become larger until, I would say explode, but non-scientifically say explode. And so I thought it was a breach on the cell membrane. But as we did more of the work, and particularly when we looked at the transcriptome and what was happening on a gene level, what seems to be happening is that the nanoparticles seem to break down any way that or I should say stop or eliminate the various mechanisms that the bacteria has to generate energy. So aerobic energy, anaerobic, and then they go to alcohol, they go to various other mechanisms, and they all seem to be stopped. And so it's almost as if any way of staying alive, I guess, is stopped. including DNA formation and various important proteins that need to be made, they're all inhibited. And it looks then as if the bacteria then just may think a new philosophy, I think, for bacteria is that they commit suicide in order to release their contents for other adjacent bacteria to survive. I don't know that that's happening, but the cell at some point, the bacteria at some point programs itself to autolyse, and so it explodes. So, and I think that with the hydrogen peroxide, it may simply be permeable to the cell membrane, so it literally just falls into the bacteria.
Yeah.
And with the nanoparticles generating lots of that, and then becoming close to the bacterial surface, it then kind of just pours hydrogen peroxide in, I think, and it loses its ability to form energy. Incredibly fascinating.
It is. It really is.
And what's really good, just interest to me, but was that I didn't know what to expect. I was really excited to get the genetic, the transcriptomic data to work out what was happening, and I thought you'd just see something. You'd see how the nanoparticles are just destroying a bacteria, but what you see instead is a bacteria that's trying to survive.
Yes.
And I thought that was incredible, and it makes sense, seeing as they've been around for millions of years, But you know, it's just, okay, that's blocked, okay, let's try this, that's blocked, okay, let's try this, and it's just this continual survival mechanism that kicks in. And I thought, you know, it's quite amazing. And looking at transcriptomics and proteomics in people as well, you see a similar kind of survival the body kicks in to protect, which again, I don't know, for me, it's
very exciting. Yeah, so that was like a new finding, you know, in terms of just what the bacteria are trying to do to evade and survive, and that, you know, from what we've seen with those particles, that they're not really able to get around that, which is probably why we haven't seen any organisms yet, microorganisms of a pathogenic nature, that haven't been able to.
Everything we've looked at has been killed.
Susceptible, and so, you know, there are a couple terms that we used. So, you know, cell lysis, for example. Could you just explain to our audience what cell lysis is?
I guess cell lysis or autolysis is the programmed cell death. So it and other, you know, the other way that I explained was it exploded. Cells don't necessarily have to explode, enlarge and explode, but they literally just autolyse. So they lyse their membrane and they release their contents and die, basically.
Yeah. And the images are very interesting. So when you have a look at it, this conversation will make a little bit more sense when you see the images. So switching out of, you know, benchtop testing and into the real world, we tested the Nanozyme within a product in a pediatric dental facility. We included it as part of the paper just to kind of show, you know, just the potential real world impact that the underlying science would have. So in terms of, you know, translating what we saw benchtop to those results, could you extrapolate on, you know, kind of the broader significance in healthcare settings for high-touch surfaces in terms of what we've seen?
Yeah, so I think that study in the dental clinic is so important because, of course, we had the coupon that was coated and it was placed by the toilet for 28 days and
not cleaned, not cleaned.
And not clean. And when you look at the control, you know, where there's no coating, and then you grow up the various organisms that are there, microorganisms that are there, you see a lot of different shapes, colors, sizes, meaning there's lots of different types of species there. But then when you look at the coupon that's been coated with the Nanozyme, we found there was no growth. So after 28 days. So it's obviously remains residual on the surface. You know, it remains active. And it also, very importantly, is able to eradicate a number of different types of species that are generally found within that healthcare setting. So.
Yeah, and we picked the dirtiest place in that it was a pediatric dental facility too, so think little kids trying to use the toilet. We literally picked the dirtiest place that could go, and it wasn't clean. And so just to put it into perspective, usually you do test and they're more controlled and they tend to be cleaner. We did not control for the amount of fluids that would hit the coupon. So, and that's in healthcare, that was a pediatric dental facility. So thinking outside of healthcare, there's other places where you can get sick. So just kind of thinking broader implications, what this might mean for like airports or gyms, when you think about, preventing illness.
Yeah. So I think anywhere where you have a lot of people, so you've got a lot of people touching the same surface. So as you mentioned, airports. I always think of cruise ships because of because of the association with illness sometimes on those. Cruise ships, schools. I mean, it could be anywhere where there's a lot of people touching, and where you've got a lot of maybe with schools as well, because you've got a lot of kids with a lot of bugs. So it could be very helpful in a number of places.
Yes, and we did learn from that pediatric dental facility. They don't always make it into the toilet. So there's many reasons that we want to control microbes in certain settings. And then so thinking about, the nanozyme, I know sometimes there's concerns around, nanoparticles being unsafe or certain chemistries being unsafe. Or that it might have negative impact to the environment. So from your point of view, could you just kind of talk to, safety, environmental, kind of like from your perch, how you see that having a potential positive impact?
I think it has a positive impact compared to the other products that are currently being used and flushed down water systems and that type of thing. Number one, because it's a coating that's residual, so it will stay there, so you'll end up using less than you would for other products. And then number two, in terms of safety, silver is recognized as safe. We have off-the-shelf silver products that we can buy. It can be dangerous in high levels and cause argyria, but generally it's safe and under moderate amounts. And the cerium oxide nanoparticles as well have been shown to be safe and are available in many products, that everyday products that are in our homes. So I think it's safe, and then in comparison to the products that are currently used, it has many added benefits.
Yeah, and I think even thinking about just washing chemistries down the sink, it goes into waterways, aquifers, into lakes, and has unintended consequences in those areas where we probably don't want to kill off microbes too. So it's kind of I know that we focus more on preventing illness, but I think that there's downstream effects that I think aren't always front of mind, but are also important to just quality of life for people. So kind of related to that unintended consequences, right? Antibiotics are often used to try and prevent infections in people, but they've caused other issues as well. So could you talk to how, products that make use of the nanozyme could help with issues around antibiotic resistance, which is becoming a growing problem worldwide?
So at the moment with our nanozyme, we haven't seen any resistance, which is fantastic. And I wonder if that's to do with the autoregenerative properties. Maybe it's the fact of its hydrogen peroxide that's released, that we're seeing comparably less, if not none at this point, resistance. So in comparison to antibiotics, where we are seeing it, and we are seeing that rise in resistant bacteria, I'm hopeful that the nanozyme will be able to not add to that and not cause resistance. And in fact, when we've looked at it with MRSA, and we've looked at it with Pseudomonas aeruginosa, which is on the list of resistant bacteria, we found that it's very effective, and so at eliminating those. So it's an exciting product, I think, for the future, as you know better.
There's the programmed death. I still, like, when that data came back, I was like, wow, it really kind of opened up what was really happening at that microscopic level.
Because I have a whiteboard at home, and I literally had to write everything down because I was convinced it was an adhesion. And I don't know if it is, it looks like it's adhering. We haven't shown that yet, but I thought adhesion, somehow mechanically breaking the membrane. And then I was going through, but what is this programmed cell? Why would it be programmed cell? And then, and I thought, hang on a minute, there's things here I'm just assuming that have happened, but I can't prove. And so then it was just this almost, ping in my mind one day, saying, maybe something else is happening. And so I had to rethink the whole thing. But I think we got there in the end. It's definitely, I think, more of the suicide and due to loss of energy and probably important protein synthesis.
Yeah. And I think also just being able to, as the number of infections that we could reduce in the first place, right?
Yeah.
So there's both the, not causing resistance, because, quaternary ammonium compounds, or quats, as they're often called, layman terms, which is in a lot of disinfectants. There are resistant organisms now to quats, similar to antibiotics. So we obviously wouldn't want to add to that issue.
Yeah.
But then I think also just reducing the amount of illness that requires antibiotics, so people are not, using that and potentially creating resistant bacteria in the body. So I think for multiple reasons, having these alternate non-chemistry, non-pharmaceutical solutions to help deal with that is a worthwhile cause for us to go after. So looking ahead, right? Because we've been working together for a while. We've have done research together. What's next? What are some of the things that you're excited about when you think about what these nanozymes can do?
I was going to go off on a tangent then.
You can do that too, actually.
So I think one of the maybe it's a closed channel that I'm thinking about, but I'm thinking about the proteins and the attachment and on the surfaces, and I think it'd be great, or maybe what I should say, scrap that. What I should say, I think, is learning more about the mechanism of how they work. I think both the serum oxide nanoparticles and the silver, and how that's functioning, in order to know how it's working at a material level, in order to then work out if we can make it even better.
Yeah.
I think would be really exciting to do.
Yes.
One of the things I forgot to mention earlier was that we did look at it in terms of biofilm as well, and again, just referring to how it's working and how the electron transfer and the ROS and the various other things are forming. I'm not sure, but it does break down the biofilm.
Yes.
And it does break it down and eliminate, I think, if I remember the data, pretty much all of the bacteria that's within the biofilm, both gram negative and gram positive. So that's really exciting. So I think maybe understanding a little bit more about how it's working, and then can we tweak it to work even better, faster, more, would be next on my list.
Yeah, because then the implications for that, outside of just environmental surfaces, but potentially for like implants in the body and other places where biofilms wreak havoc on surfaces that you touch when you go into hospitals and other places, but they also wreak havoc if you have implants or other external objects put into your body for healthcare purposes. And so there's a lot of fruitful avenues that it's almost too much sometimes, just all the places it could be helpful.
Yes, it is. And I think, coming from the orthopedic world, I'm kind of knocking myself for not thinking about that, because it is a huge problem. Biofilm formation adjacent to orthopedic implants, but also other, as you mentioned, catheters and various other things that are put into the body. It's a huge problem. We need something that can break down that barrier and, like we say, kill those bacteria inside.
Yeah.
And so if we can formulate something that can be used internally, then that would be
yes,
and it'd be phenomenal.
I have a feeling you and I may be working on that at the rate that we're going. So in terms of, just thinking about the impact to healthcare, in terms of, so going back outside of the body, environmental surfaces, how would you view this technology being applied to surfaces helping with infection control in healthcare? So now this is more the clinical aspect, translational aspect of the research.
I think that this is important in terms of applying it to surfaces, applying it to in healthcare settings, applying it to chairs, to curtains, to walls, to floors. And then I think as well, one of the things that we've looked at as well, in areas where there's sunlight, or where places where it's cold, having a broad application that is effective and lasts days, if not weeks, if possible. So and therefore, if it stays there, you have multiple people coming in on multiple occasions, and you would remove that transmission, and also save the cleaners.
Yes,
from cleaning. Often.
Less chemistry, less manpower, hopefully, and more sanitation. Yes, safer surfaces.
Yes.
As always, it is always delightful to speak with you.
And you too.
So as we end our interview today, what's one takeaway you'd want to give to the audience here listening to us?
So my one takeaway would be, I guess probably knowing that bacteria are around in our environment can be a bit scary. Most times our bodies can fight them off, most occasions. But I think that it's important to have these coatings, just to reduce getting ill, reduce, having family members getting ill, reduce spreading more troublesome bacteria such as the MRSAs and such as the pseudos. And so it's important to have that layer on surfaces just to, to help to reduce, and not only in healthcare settings as we've talked about, but also in schools, airports, cruises, wherever it might be, so that we can kind of reduce or control the transmission, particularly of those nastier products.
Yes, and I'm sure parents of young children will agree with you, even if they don't understand what a bacteria, a biofilm, or a nanozyme is, just because of the number of surfaces they touch, and then they put their hands in their mouths. But yeah, so really, really great insights. Thank you so much for breaking down what some might view as a hefty literature paper to help educate our audience. And so, thank you for listening, and we hope you learned something today, and, take care of yourself, stay healthy, and we'll talk to you next time. For our listeners who want to dive deeper into the conversation today and the technology we're discussing and the results that we've discussed, please click on the link below. That'll take you to the paper so that you too can become more educated on biofilms and their impact, and how nanozymes can help deal with those. Make sure that you follow and subscribe Kismet Tech Talks. And if you have more interest in terms of nanozymes and certain products, please visit our website to learn more. Thank you.